Welcome to this session of Shadow the Scientist. My name is Jamika Marshall, and I'm pleased to serve as the coordinator for the STS initiative. And, we are led tonight by Dr. Brian Lameau. Brian!
Hi, Jamaica. We got 2 hours of potentially, unfortunately, closed dome tonight. So it looks like the conditions on Maunakea are not great. We've just come out of a winter storm, and we have about 70-mile-an-hour winds up there.
About that.
Currently. And so our opening condition is
or for the rest of the world, we're sitting around 23, 24 meters per second, gusting to about 30.
Yeah. So very, very high winds up on the summit. It is gorgeous up there. So let's see, can you see it? Okay, so barely, you might be able to barely see above Charlie's head or over by Kenny, these really beautiful images from the summit of Mauna Kea. These are taken from our telescope. They're not with our telescope per se, but they're cameras that are mounted on our dome. And they're pointed up north towards Hilo, where we are at the base facility, to the east, south, and west. And so we're just entering into twilight right now. Sunset was about an hour ago-ish.
Oh, we are twilight. Nautical twilight is over. We're in astronomical twilight now.
Okay, yeah. So we're just getting that there, and so normally we would be open at this time, observing with the beautiful sky. You can potentially see some of the. It's hard to see, but yeah. So there's some stars rising. It looks beautiful, but unfortunately the wind is going to keep us closed at least for now, and we're going to keep an eye on it. We have some really great weather monitors up there on the summit. And we'll keep an eye on it and see if we can open at some point. If we do open, I think we have some exciting plans. We're going to get our near infrared integral field unit spectrograph up and running. This will be the last time. This will be its last voyage on the telescope. So this is an instrument that's been around for quite some time now, over a decade, I think.
It's actually, and it's the newest. It's our newest facility instrument, actually.
Yeah. But we are going to retire it because we have some capabilities that we've upgraded on another instrument called GNIRS, which basically match it. And so we're going to make room for another instrument that's coming, which is called IGRINS 2. So that's being commissioned right now, and commissioning means that we're getting it ready to accept it at the telescope. So we're checking all the specifications of it, and then we will accept it as a telescope, and then we will mount it on our telescope. What's that?
Accept it as an instrument.
As an instrument, yes, yeah. And then we will mount it on our telescope and use it for science eventually. Yeah. So that's the plan. But for tonight, we would take our first astronomical images with this NIFS instrument, probably over a year.
Longer than a year. It was not on over the summer, so it would have been.
Yeah, I think it's September 22.
A year and a half.
Yeah.
A year and a half at this point.
We put it on Sky, and so we're very much hoping that we can get open tonight and take some images with it. And if we are able to open up and take some images with it, we'll calibrate it, and in fact I'll be in charge of that calibration, and then we would actually take science with it immediately. So we would take scientific observations with it just afterwards.
I'm hoping that that you all do get a chance to open so we can get a peek at some actual science tonight. That would be amazing. But in the meantime, while we're doing that, it is thrilling to see you all in the control room and to at least get an idea of the observing plan for the evening.
IQ85 plan has a couple of NIFS observations.
Me too.
Yeah.
So while we're waiting for that, maybe so I can introduce myself since I've been talking already, and then we could have other people in the observing room introduce themselves. So my name is Brian Lowe. I'm a staff scientist here. So I work with all the different instruments, the instrument teams here. My main job, beyond my research that I do with all the telescopes on Maunakea and telescopes in space, among others, is to try to get the most out of the observations that are taken with Gemini North. And so I help scientists from around the world develop their observational plan for their scientific goals. And we work together with those scientists to make sure that their observations are as efficient and set up in a way that maximizes the scientific return of those observations. And then I will also help get instruments ready. I will also observe, although I don't observe as much as other people in this room. And I will also do other functions for the observatory that are kind of administrative. So that's my basic role here. Garima, did you want to introduce yourself?
Sure. Hi, I'm Garima Singh. I'm the adaptive optics scientist here at Gemini North. And I also represent GPI2, which is Gemini Planet Imager. So this instrument is, we're going to receive this instrument at Gemini North in roughly a year. And this instrument will take direct images of exoplanets. So these are the planets that orbit stars other than the sun. So my role is basically to commission this instrument and make sure that both the science and the technical requirement of this instrument is met. So this is kind of like what I do here. I'm gonna pass on to Charlie.
Hello, my name is Charlie Figuera. I am a radio astronomer, but here at Gemini, I work as a science operations specialist. That means that I am one of the crew that operates the telescope, that observes with the telescope. We have a two-person night crew, and we split our roles up, and we can talk about that a little bit later, but basically we are responsible for actually controlling the telescope, controlling the instruments, the various cameras, detectors that allow us to collect data. And I'm sure it'll be more about all of that as we go on.
Absolutely. Yep.
I'm Jenny Burkheis. I'm an operator tonight. I also have the same job as Charlie does. And tonight, my responsibilities would be to point the telescope, detect the telescope, and set up guiding.
Yep. So the SOSs generally keep us observers in check. When I'm on the telescope, I don't know what these guys know. These guys know everything about the telescope, and she's not kidding about protecting the telescope, because I will open up under almost any conditions. I'll try to get the observations, and SOSs are here to say absolutely not. That would be horrible for the telescope. Please don't do that.
You betray your experience at Tech, I think.
It's classical observing, so yeah, it's a little bit different. Yeah.
Thank you for that wonderful introduction, Brian, Garima, Charlie, Jen. Absolutely wonderful. We are so thankful that you're allowing us to shadow you this evening. And so I'd like to welcome everyone who's in the chat with us, starting with Miss Peggy Lamo. We also have Avinash, Rakesh, Lisa, Rob, and Mashael. Thank you all for joining us. Please feel free to leave comments and questions in the chat at any time, and we will get to those as we can. And since we're not quite open, as Brian was explaining and Charlie was explaining, we have time to really get into a lot of discussion about operations, instrumentation, any questions that you may have. So please feel free to drop those in the chat. So maybe we can start with the weather. So it's a nice evening, but you're closed because of the wind speed. Is that correct?
Yeah, that's right. So let me share.
Nice evening where?
Good
So
question.
it's beautiful. We can see stars.
Yeah, you can see stars.
You can see stars. That's nice. That's always a plus. But yeah, so if you look, this is from the Canada, France, Hawaii telescope. And so these are tools that we use among the tools that we have for ourselves to assess the weather conditions. So again, we're at about 200 feet above sea level here in Hilo. So we're not on the summit of Maunakea. And so we have to understand remotely what the conditions are up there. And so there's all sorts of sensors up there that allow us to do that. And so this is a kind of strip tool or a readout of what the various conditions are up there. And so from top to bottom, it's temperature, relative humidity, pressure, and wind speed. And the units on the wind speed here are miles per hour. And so our opening condition, if you can see my cursor, yep, is right around here. So around 50 miles an hour, and we need that sustained for a while. And currently we're sitting at about 55 or 60 miles an hour. And so I think, what are we, 20 minutes or half an hour sustained 50-mile-an-hour winds or below?
We're below.
Yeah.
Ooh.
Given the conditions the past few nights, we're going to play it very conservatively.
Yeah. Yeah.
The problem is that the high winds put lots of loading on the dome and on the shutter, so that if you have, so that loading is transferred to the actual wheels that turn the dome around. If you open up the shutter, that turns the dome into gives it a lot more sail area. Basically, it collects the wind a lot more, and so that puts a lot of stress on the dome, on the telescope inside. So we have those wind limits to protect the equipment.
Yeah. So our goal here is to do science in perpetuity, not just do science tonight.
Correct.
And so it's nice to have a working telescope for extended period of time. And if we were to open up tonight, perhaps that would affect the chances of opening up tomorrow night and in the future.
Yeah.
And this is why
Exactly.
the SOSs are here, and they're extremely well trained to let us know exactly what the opening conditions are. And we always play conservative. So the limits are conservative. Even opening up within those limits are conservative. Because the goal is a large temporal baseline of science, not just science on a given night.
Right.
And because the wind conditions are fairly bad, that also causes fairly serious issues with the spread of the light. Our ability to observe something, to resolve out something in the sky, changes with the conditions on the ground. There's ground layer turbulence within the dome, above the dome, and then in the upper atmosphere, some of which we can correct for using our adaptive optics system, some of which we cannot. And so when the conditions are this windy, it makes it less enticing to observe because the data quality will be less. And so that doesn't necessarily factor into our decision-making process. For every single night that we observe at Gemini North, we have what we call variant plans. So we have, for every single set of conditions, we have a plan in place. And this is there's a specialized role at the observatory called a Q coordinator. So Q is the pool of astronomical observations that we could potentially source from on a given night. And so for every set of conditions, if we're open, so different water vapor in the upper atmosphere, differing amount of clouds in the sky, differing how much the atmosphere spreads out the light that we're seeing, and varying other conditions. We have a scientific plan for that. So as conditions change, we are required as an observatory to shift our observations to that particular variant and take those observations. Of course, there's some play and there's some art in all of this, but we have, I think, so for tonight, we have something like probably upwards of 12 plans in place, depending on the conditions, if we were to open. So it's an incredible amount of work that our Q coordinators have to do to get everything ready during the day so that we can observe at nighttime if we are open, and we can get the most out of the observations that we can take.
Wow, that definitely seems like a lot of thought planning has to go into all of those details and plan A, B, and C, maybe even a plan D just in case for all of the potential possible outcomes for any given night. As for the Q coordinator, is that a role that rotates around everyone in the on the observing team, or is there one person who um, wears the hat for that role every night?
Yeah, so that would be way too big of a job for one person. This is a job that various members of the scientific operations staff take on for roughly anywhere between like 3 and 6 days. And so the job is a very, very crazy job. You have to be on call all night in case there's issues with the plan at nighttime. You have to be bright-eyed, bushy-tailed in the morning. We have a 9:30 operations meeting, and the Q coordinator has to be prepared for that meeting. So it means they even have to start at about 7:30 in the morning. So on call all night, start planning for the next night at 7:30 in the morning, then go to our 9:30 operations meeting, deal with any issues that came up with the previous night, let the entire staff know of a science highlight that happened the previous night. So not everybody at the observatory is working nighttime. We're taking observations for other people most of the time. So we don't necessarily know the precise science of what we're observing. And so the Q coordinator acts as kind of a lens to focus that for our staff. And then they spend their entire day planning out different variants and anything that comes up during the day in terms of instrumentation needs or changes. So they always have to have their ear to the ground. They have to listen to our day crew. They have to listen to our night crew. They have to be fully engaged with everything. They're the kind of central node for the observatory at that point. And so you can imagine that's an incredibly taxing job. And so that is shared amongst the science operations staff. So SOSs have been QCs in the past, not all of the science and astronomers. So for example, I'm not trained as a QC, so I'm doing other work for the observatory. I have heard rumors that I may be trained as a QC sometime in the next month or two, which I'm not looking forward to. Yeah, so currently we have somewhere in the neighborhood of 8 people or so that share that position, and they switch off so that they can take a rest and maybe get some sleep at some point. And so just to give an idea of like what they do or how this Q operations works is so every semester we have 2 semesters. Every semester there's a group of scientists that are pulled together to determine what observations might be the most scientifically interesting for the observatory. So people from all around the world send in proposals. They say, hey, I want to observe this thing with this instrument, and I think that it will answer this question. This group of scientists then anonymously reviews these proposals. So it's dual anonymous. The people reviewing don't know who the people who submitted the proposals are, and vice versa. That group of scientists then ranks these proposals. And from those ranks, we create a pool of potential observations for that upcoming semester. And we even rank within the proposals that pass the threshold of potentially being observed. So I think currently in this past semester, roughly 1 out of 5 proposals made it through. So it's highly competitive. About 20% of people who propose actually make it into this pool. And then we rank something called band 1, band 2, band 3, and then band 4, where band 1 is the set of proposals that were determined to be the most scientifically worthwhile, band 2, second most, band 3, third most, and so on. And then the Q coordinator takes this giant pool of potential observations and determines for each set of conditions what would be the most scientifically interesting. And so I can, let's see if I can bring up the Q-plan.
And while you're doing that, thank you so much for that insight. While you're doing that, I dropped in the chat a link to the 23B Q summary for bands 1 through 3 programs, and there's quite a bit of information here. We can see it looks like the status of most of these are complete. A few that are not. So when proposals get accepted for observing, do they all get listed here under the Q the Q summary?
Yeah. So they should all be listed up here. And along with the how much we've observed them. And so, yeah, this is really helpful for our scientists who propose. They can come on this page and see how many observations we took, when we take them, so on and so forth. We also have an observing tool, which is a way that we interact with the scientists. So we create observations together. I can show that a little bit later. But that combined with this page helps people understand what the status of their scientific observations are. So people take these observations and then they analyze them and they publish scientific papers with them. And so of course they want to know, immediately when we take the observations that those observations have been affected to some level. Even if the completion is not 100%, a lot of times even a 20% completion can give some science for our investigators, for the scientists that propose and are awarded time. And so we always send out an alert, an email to the investigators saying, hey, we just took an observation, take a look at it. Here's all the tools. As an observatory, we provide tools for them to analyze the data, to get it into a form that they can analyze it scientifically. And so we provide those tools to them so that they can see if they can grab some science anytime we take an observation.
Fantastic.
Keck Observatory, I think, is shooting off a laser.
Yep.
Amazing.
That was a question I was asking, like, why Keck is observing.
Yeah.
I don't know.
Well, wind speed at Keck is at a slightly lower elevation. We are essentially at the highest point on the Maunakea summit. And wind speeds up here are typically much higher than they are anywhere else.
Yeah.
So down by Keck, it's sitting around 10 meters per second or so.
Oh, really?
Oh, yeah.
That big a difference.
Yeah, it's that big of a difference. Whereas up here where we're at, it's, we're still sitting around 23 meters per second, sustained up to 30 gusts.
We're on the ridge, they call it.
Yeah.
Get hit with the weather first, usually, as long as it's not fog coming from the bottom up, which usually comes from the other side. In the valley.
Oh,
Right. If stuff is coming up from the inversion layer, they're lower down and will often get hit first.
Yeah, I see. So Subaru's at 26 miles an hour, so basically half.
Yep.
Oh, I didn't realize that.
I didn't realize that either. And that leads into, it's a great segue into a question we have in the chat from Avanish. Avanish asks, what caused the sudden drop in the relative humidity, the percentage of relative humidity between 3 and 6 o'clock? Any ideas?
Ooh, that's a tough question. So 3, 6.
It's like it also happened at a sudden rise of pressure. A little bit of a drop in wind speed. Right?
So that's
So
dropping
let's
the
say-
range.
Yeah.
Yeah, the pressure was dropping. Wind speed was kicking up a little bit. Temperature was basically constant. I'm not sure. I'm not a weather scientist.
Is that 3 a.m.?
Sorry, I
Referring to 3 a.m.?
They're looking at
Avanish, please feel free to unmute yourself. Was that 3 p.m. or was that 3 a.m. or earlier today, Avanish?
From the provided graph, it was 3 to 6. There was no other explanations. Yeah, okay, it's 3 a.m. to 6 p.m.
Yep, that's morning hours.
This one here.
Yep. Well, we did see, my guess is that we see a moderately sharp temperature rise at that same point. And so as temperature goes up, relative humidity will drop since warmer air can hold more moisture. That begs the question, why did the temperature see that rise right there around, 3, 4 o'clock in the morning? Don't know. Wind conditions are often, our conditions tend to be fairly stable here at the summit. As long as we have what's called an inversion layer, which is sort of a atmospheric boundary that usually sits down closer to 3,000 meters, summits at 4,000 meters. And that helps keep conditions very stable at the summit, but nevertheless, things can shift. And so we will see some nights, particularly when there's a lot of atmospheric turbulence, where temperatures, humidities will shoot up or down. That's part of the reason why we're going to play it very conservatively tonight. And not just wait to get below the wind threshold, but wait till we are quite a bit below the threshold for a long period of time, because we do seem to be a very variable weather conditions tonight.
So it wasn't really anything causing it. It was just a random occurrence, right?
Something caused it, but nothing that we can track with the resources that we have at hand.
I see. Thank
Yeah,
you.
I think we were well closed at that point last night, right? So you guys
Yes.
weren't monitoring.
Yeah,
at
in
that
fact, we called the night around 2200, 10 p.m. last night, because the wind conditions were well above the threshold and had no indication of coming down.
It looks like it was a good call. Based on that.
It does. Looking at the mediogram today, it never went down. So we got a little more sleep than we would have, and did no less science than we would have.
Exactly. Yeah.
Sometimes it feels like we're in a wind tunnel or a weather tunnel that passes right over the island, and sometimes it goes just north of us. And as it starts to shift south, our weather will very suddenly change, either with cloud coverage or temperature changes like that.
We have our location here gives us a couple of different prevailing weather directions. Jet stream directions are west to east, but our trade wind directions, the lower level winds, are from east to west. So we kind of have to be on the guard for things moving in from different directions. And that can make for some turbulence and variability.
And I can also add that Gemini telescope is relatively lightweight than as compared to the other telescopes. So such high wind condition also introduce vibration into the instruments. So the optical elements kind of vibrate, and that basically creates image motion. So you don't really get good image quality.
Degrading your data.
Yeah, degrading data.
Why did they make it so light?
Good question.
And I'm sure light is relative because the telescope is huge and I'm sure very, very heavy, but light and relative to other things, to other observatories possibly.
Yes, yeah, that's what I mentioned. It's relatively to other observatories. Gemini telescope is lighter weight. I don't really have the numbers to
Well, I'd expect us lighter than Keck, since we're a little smaller than Keck.
But they also don't mount the instruments on CAC, but for the most part.
They're all
There are like, a lot of
Smith.
a lot of them are now Smith, yeah. So we mount our instruments on the back of the cascade.
Right.
So yeah, I don't know, but our instruments are also light, like as compared to the Keck instruments. This is why we can't do like massively multiplex spectrographs or large field of view.
We're limited in the size
Exactly,
of
yeah.
instrument we can support off the back end.
Yeah.
Are they newer instruments by comparison to Keck?
Our instruments are much older than Keck's in general.
Older and
Yeah.
lighter, that's surprising.
Yeah.
I thought they'd get lighter.
Keck's instruments are enormous.
Their capabilities are ramped up in the sense that like GMOS, for example, which is not that new. I mean, it's 2003, so it's not that new, but it's a behemoth, and the field of view is much larger than GMOS, for example, and the multiplexing is greater. MOSFire also is a huge instrument. Multiplexing is more than like F2, for example, by far. You can fit, I think, 43. It's 43 configurable slit units on MOSFire, as opposed to maybe 10 or so on F2. But Keck is a single instrument for the night, correct? No, they switch. So they've actually moved to a model where they could have up to 3 instruments on a night. Yeah, so they break up. So Keck is classical observing. So classical observing is different from what we do here in that a scientist is assigned a night or half a night or a quarter of a night, and they are assigned an instrument, and as long as that instrument's up and functioning, then they use that instrument, and then they are given kind of free rein within limitations to weather and the telescope capabilities to observe what they want to observe. So whatever they think is best scientifically for them, they observe. And then they if it's half night, then they hand it off to the second half observers, which could come from a different university, totally different science goals, so on and so forth. They do an instrument switch. That instrument switch typically takes about 10 minutes or so, as opposed to us that takes 30 seconds. I mean, way less than the slew time,
right?
Usually. And so it's fairly lithe, but it's not as
nimble as we are.
Yeah. So we're really the quick telescope, and Subaru that's even a filter change on the Hypersuprime cam is like a 20-minute movement.
Yeah, and they tend to do it during the day, plan for the whole rest of the night.
Yeah. And if you're a classical observer on Hypersuprime cam and you have multiple nights, you're trying to minimize the number of filter moves you make. So you might do like one all G band one night, then all R band the next night. So yeah, definitely not as fast as we are. But then you get a enormous field of view and a single observation. So
right.
It all depends on what your science goals are.
And so when we think about the science goals, is that one way that say with Q observing, which Gemini does, is that one way you determine what you're going to look at in the evenings, the science goals, or does something else determine what you're going to look at? Let's say if we didn't have these high wind speeds, how do you go about choosing that? And I think you said the Q coordinator certainly plays a huge role in that.
Absolutely, yeah. So it's a very complex calculation. So I think probably the first thing that we would look at is the moon phase. So the moon phase kind of determines whether we're going to be observing in the optical for some portion of the night or the near infrared. So we have near infrared instruments and we have optical instruments. And in the optical, especially in the blue, the moon is very, very bright when it's full. And so we don't observe in the blue, for example. We could observe in the very red of the optical or the near infrared, but generally we would stick away from the optical. If it's a new moon, we would almost certainly be observing in the optical. And so that would be another set of instruments that we use. And that's kind of the same for every observatory. So if you look on like Keck's schedule, they're not going to be planning super blue observations when there's a full moon. Now, it just doesn't make any sense. And so they try to mix and match such that the best instrument is on the sky given the moon phase. And then after that, it's kind of all over the place. So of course there's these. So I have this Jamika, if you can pin this video, the screen I'm sharing, this is one of our operations computers. So where my finger is here.
Got it.
So this is a Q plan, and so you may not be able to see it, but this is just from September of last year. And let's see. So this is just one of our so-called variants. So we have on the upper left here, we have something like 12 different plans, and this is all created by the Q coordinator. And the Q coordinator goes in for every single scientific program and asks the question, what did that program ask for? So if for their scientific goals, what conditions did they need? And so this particular one here is set by 3 conditions. One is the image quality. So this is the blurring of the light by the atmosphere and the ground layer turbulence and everything else. Also the thing that Garima mentioned. So the wind shake, we can have even parts of the instruments that we're using mechanical cooling in some cases, and so that can shake the entire telescope. Garima has to deal with this because Garima does extreme adaptive optics, and so she has to take into account all these different vibrations, and all these different components. So image quality is what we naturally see with our instruments. So if we just point on the sky and we see the blurring of the light of a star, let's say a point source, and this will tell us the image quality. And image quality 85 means the 85th worst percentile of image quality on Maunakea. So if you averaged over an entire year, only 15% of the time would be this bad.
Would be worse than that.
Worse than that, yeah. This bad or worse, yeah. So that's we define these in percentiles, and so IQ is image quality. You probably can't see that at all, but image quality 85, so it means fairly bad image quality. This next one is cloud cover, so CC 70. So again, 70th percentile in terms of how bad it is. So 30% of the time it'll be this bad or worse. And then this last one is water vapor. So the amount of water vapor in the upper atmosphere, this does matter for mid-infrared observations. And so this is water vapor 80. So meaning a fairly high concentration of water vapor in the upper atmosphere. And so we have starting at, so this is HST, at 7 o'clock at night, we have the Q coordinator has put in a plan of all these different scientific programs here. So you can see an arc like this. This is this particular object. So this particular object is this target name, doesn't matter, but some astronomical object, and it's rising in the sky in Hawaii, and then it's reaching its highest transit point, and then it begins to set. And so we have to, of course, be cognizant of this because we only see a certain portion of the sky at certain times of year. And so we want to observe these targets as high in the sky as possible because the amount of atmospheric blurring and the amount of extinction, so the removal of the light from the atmosphere, is gets better the higher the object is in the sky. And so so the Q coordinator has to put together a plan that kind of maximizes for all these observations. Each one of these is an individual scientific program with an individual target. For all these observations, how do we observe them at the best possible conditions, best possible location, given their observational constraints? And so the observer at night, so this is Charlie for tonight, they can move this around. So they can say, okay, well, I'm not going to observe this one at 1 in the morning as the Q coordinator asked because we're behind schedule or because something blew up in the universe and somebody else is like, oh my gosh, we got to go see that. So that's another part of observing that's super exciting. The universe always surprises, and we have actually programs that are set up for surprises. So a scientist will propose to Gemini Observatory and they'll say, hey, once this surprise happens, I'm not sure exactly where it's going to happen, what exactly it's going to be, but as soon as something happens that I'm surprised by, I want your telescope. I want to see it. And so they can do something called trigger, which means that they say, I really would like to see this thing right now. So we have a rapid trigger, which basically by policy, we should make our best effort to observe that night when it's triggered. So if they say, no, this is really important, we want to see it, we make space for it. And so let's suppose that something blew up and at midnight, and we have to switch things around. So we have to say, okay, we're going to finish up this observation that we're taking now. We're going to move to this place in the sky that this person is surprised by. We're going to take an observation. That observation takes an hour. Well, now we're at 1 a.m. Instead of at midnight. So we have to shift everything. So everything shifts over. And so the observer at night has to play, this kind of three-dimensional chess with all these different observations, and determine, okay, should we skip some? Because you can always come back the next night and observe unless it's a temporally occurring phenomenon. So a lot of astronomical objects are constant on human timescales. And so we can come back the next night and observe, potentially. So we say, okay, maybe we'll forego this particular observation or forego this particular observation and instead concentrate on this one. And then so on and so forth. And so it's nonstop adapting to what the conditions give us and also what the universe gives us. So, a lot of times we can slew to a target. It may not be there, it may not be as bright as we think. And so the observer has to adapt on the fly as to, what best guess, do we need to open the camera shutter for longer, or do we need to move the telescope to a different location in order to see that particular object? And so it's very dynamic. When everything is going right, then as an observer, you're just clicking and you're saying, okay, set up this instrument, move here, observe this target. Okay, let's move on to the next one. Great. And those are the awesome nights. Then you have time to actually read what people are proposing for, what science you're observing for, all this kind of stuff. But a lot of nights it's the wind changes speed or direction. Even direction can matter. The clouds come in. The image quality can degrade or get much better, and so we try to again make the maximum amount of scientific yield for the observations. And so on nights that are very unstable like tonight, if we were open, we'd probably be changing around quite a bit the plans. If we were open.
If we were open, we'd probably be sitting at the bottom end of the queue, to be honest, of the variance, I suspect.
Maybe, unfortunately, we can't get a measurement.
That's an incredible amount of change and dynamicism that you have to take into account every evening. It's no wonder you have a team of running things for the evening, because it sounds like there's so much that one person in these different roles have to play, especially the observer, which for this evening I believe you said is Charlie. So
That's right.
when you're looking at, for example, this high wind speeds, who makes that decision, the determination to say we're going to stay closed until the wind speeds come down to a specific targeted amount? Is that everyone that we were seeing in the control room? Is that one particular person? Does it have to be a consensus? How does that work?
Generally, the operator, played tonight by Jenny, is responsible for telescope and instrument safety. So they have the word on whether or not conditions are safe to open. That includes humidity, that includes wind speed. There is also generally consultation between operator and observer, though. There's a lot of shared responsibility, but ultimately that call is typically made by the operator. That's part of their role or their primary responsibility in keeping an eye on the equipment. the observer is going to be, I think Brian did a great job of explaining, the primary responsibilities of the observer. We're looking at weather too, but less from a safety perspective, more from a how do we get the best science out of the current conditions that we can.
Okay.
But I
Okay.
would add to all this is that there's a huge, so there's night operations, but there's everybody that sets us up for night operations.
Absolutely.
There's the day crew that goes up in these crazy conditions. In fact, there were people up there today working on one of our instruments in insane conditions up on the summit where it's 0 C and 70-mile-an-hour
The
winds.
conditions were a little bit better actually
But
for a bunch of today, but
it's still crazy.
but it's still unpleasant.
We're in our nice, well, sometimes it gets a little bit cold in here, but nice air conditioned room, like doing our thing, whatever. But they're driving up to 14,000 feet and doing their thing, with 60% oxygen and working all day up there. Then we have people that develop instruments that work on the back end that work with our partner countries or partner institutions to develop new capabilities. So GREEM is part of a team that does that for our capabilities coming up in several years from now, 2027. 1 year?
GPI 2 is in a year.
Really? Yeah. Oh gosh. Okay.
It was supposed to be June and July of this year. Now it shifted.
Okay. Yeah. 1 year. How confident are you about 1 year? Because
80%.
80%. Okay. So we've almost finished the GNIRS IFU project, and that I think the LR IFU was 2.5 years overdue.
Wow.
So we're at the 5-year mark.
Yeah, but it's GNIRS.
It's GNIRS, yeah.
Everything it takes longer with GNIRS.
Yeah.
We're waiting for the detector for GPI2. If we don't have the science detector, then that's a different story. But for commissioning, we can in 1 year we can do commissioning with GPI2, but probably not science if the detector is not ready.
Right.
Yeah.
So a year.
Okay. So a year.
Today.
Yep.
As of today.
Okay. So 1 year from now. But there are projects that are on timescales of even 5 years, 10 years. There's strategic visions for the telescope, for the observatory, and we're hoping that those are seen through.
GNAO about 10 years out, maybe.
20, yeah.
Is it only 5?
2027,
I've heard
2028,
5
yeah,
years, yes.
yeah. That's the plan. GMOS is supposed to be 2028. Yeah. So. Yeah,
I'm so looking forward to
that
that.
would be awesome. Yeah, that's my wheelhouse science. So yeah, stoked on that. But yeah, but software engineers here, hardware engineers. There's a huge infrastructure for the observatory that gets us all ready to observe for the night and make these incredible instruments, all these capabilities, so that our giant light bucket can collect light that's actually scientifically useful at the end.
Absolutely. Absolutely. And all of their hard work comes down to our mistakes.
Yeah.
Our judgment calls at during the night.
Yeah, at 4 a.m. Yeah.
So, no pressure at 4 a.m, right? We do have our espresso machine in the kitchen in the back, and we do make good use of it.
Yep, absolutely.
I bet you do. I bet you do. And so you said that the day crew, some members of the day crew went up today to check on some instrumentation. Who makes up the day crew? What is their role?
So the day crew is a rotating team. So it's not, there are harsh conditions up at the summit, and so not everybody goes up every day. And it's about 40 minutes to the visitor center where people acclimate from Hilo.
At about 3,000 meters.
Yeah, about 3,000 meters, 10,000 feet. And so the day crew leaves early in the morning, goes to the visitor center, spends about a half an hour acclimating, and then drives another 20 minutes if you're lucky, up to
under good conditions.
Yeah, under good conditions, up to 14,000 feet to Gemini. And then they spend roughly about, depends on the day, but 6 to 8 hours up there.
You're up for 12 today.
12. Okay, so yeah, I mean, it can be really crazy. Yeah, so
Yeah.
12 hours. I think our maximum is 14, right?
14 hours at the
Yeah.
summit. Yep.
Yeah.
For any 14 hours in any 24-hour period.
Yeah. Yeah. It's not a place that's easy on human beings. That's for sure. And what's that?
It ages you.
Yeah, it's quickly too. Yeah. So I mean, you're just like, you have to make slow movements up there. At least I do. Slow movements. Brain capacity is not all there. You have your plan before you go up there. And I mean, Charlie, you've done a decent amount of observing from the summit, right? Like, I mean,
And it's the low oxygen content at 4,000 meters that does it. You know, you run up, I've seen people run up the stairs up there, and that's definitely not something I can do.
yeah.
You get dizzy.
I get more energy up there, to be honest. I feel like it clears my head out. But maybe it's because my body's designed for higher elevations.
Did you observe from up there,
Down
Jenny?
here, everything feels very heavy. Yeah, I've observed up the summit for SMA, Subaru, and then I've been a night attendant for IRTF.
Okay.
And anything you think you can accomplish, you can cut that in half when you're at the summit.
Yeah. Oh, that's for sure. Yeah.
Everything takes longer.
If anything goes wrong, yeah, you're. I mean, you'll be fully convinced that you're doing your calculations, right?
Oh,
You'll
yeah.
be fully convinced. Yeah,
Yes.
you're drunk on your own power at that
Yes.
point. You're wrong. You're almost certainly wrong.
But you're wrong.
And so when the day crew is at the summit and they're doing checks on the instrumentation, engineering, any the things that need to be done to make sure that you all who are running things in the evening can actually get to your science. Do they go up every day, or is it just as needed?
Yeah, usually it's Monday through Friday, although you may have noticed today is not Monday through Friday, and we did have day crew up there for 12 hours. So I mean, we have an incredible day crew that go up, as I mean, they will certainly go up Monday through Friday, but they will go up as needed. And we had an issue with one of our instruments that we're currently commissioning, and they went up there and they spent 12 hours up there. I've been out with the day crew in social situations. They'll get a call, something's going wrong at the summit. They're done. They're it's a Saturday, it's their time off, whatever. They're going straight up to the mountain and dealing with the issue. So, I mean, it's incredible. Like, I mean, everybody in the observatory is incredible because, if something happens, we'll all fill in for each other, or, we switch roles around a lot. So we, realize what the other people in other roles, what they're going through. And, if people need breaks or whatever, we have a huge number of people that are very team oriented. But, what the day crew do is,
They're
crazy.
very dedicated in the sense that sometimes you'll get calls at 2 a.m. because they woke up and they were just wondering how things are going at the telescope, and they'll call and ask. And it's like, so I don't know if they really ever stop thinking about their job and how to keep things running smoothly. It's very interesting.
It's worth noting that the day crew is, the people are generally specialized in different tasks there too. So you'll have some members who are instrument specialists, and some who are specialists in the mechanical systems of the observatory, the cooling systems, the enclosure itself, the dome, the blowers, basically plumbing related things up there for cooling. So there's a lot of specialization in that crew, software teams, and there's a lot of things that they work together on. Then there's a lot of things that they are specialized on, separate tasks within all that has to be done.
Yeah. A lot of different backgrounds.
A lot of different backgrounds. Very wide range with very different, honestly, very different skill levels.
Yeah. Yeah, I think on a previous, so last month, we had the day crew lead on, Andrew Galvin, and he spoke to some of his team members, what their backgrounds are. And I think we asked them the question, like, what does he look for? And, you know, if he has to hire somebody new for the day crew. And there was no good answer because it's, you know, it's all over the place what skills are needed. But I think the biggest one is dedication. I think that's true of anybody at the observatory. Like, you have to love this job. Like, you have to, I mean, there's no reason you're doing it if you don't love it.
Right. It's kind of interesting how few of the employees here are actually astronomers.
Yeah.
A very small fraction.
Yeah.
Which I
Really?
think is surprising to a lot of people.
Yeah.
Yeah, absolutely. I think that's that is surprising. So what would you say is the percentage of astronomers versus everyone else?
I shouldn't have said that out loud.
I didn't mean to put you on the spot at all. No, it's okay.
Astronomer, right? So like, I mean, like a traditional role astronomer, traditional, like through academia, a PhD,
PhD
doing
astronomer.
postdoc research. That is like, those roles are probably 5% or maybe 10% of the entire observatory.
I wouldn't
if
even
we're
think
lucky.
10. No,
Yeah.
not even.
I mean, up at the upper start, like like our director, for example, and our higher level, you know, administrative staff come from an astronomy background.
Yeah, I'm just thinking about the on-site people we've got. I mean, how many astronomers do we have there in the back building?
For operations, I think it's 12. Something.
12.
Yeah. That includes the science fellows. 15 with science fellows. And then that's, you know, operations is not everything. So
Yeah.
maybe another
Yeah,
4
maybe
or 5.
10%. Yeah.
Yeah.
But in that ballpark.
Yeah. So yeah, everybody else, I mean, engineers, I mean, it's all over the place. I wouldn't even attempt to classify it, but you know, everybody, but we all, one of the things you know, I came from a kind of traditional-ish academic path, kind of. But I've learned, like, you know, and I observed for 20 years before on Mauna Kea, before coming to Gemini. And coming to Gemini, I've learned through interacting with people, you know, all different roles and all different backgrounds. I've learned an immense amount of, you know, I thought I was good at observing before I came here. It's, you know, like, it's put me in my place. But I've learned a lot of new skills and you know, like, in a couple of weeks, I'm going to go up to the summit and attempt to, like, at least watch some hardware work being done. And that's not something that I'm comfortable with, that I am familiar with, but I'm going to attempt to learn so that I understand the instrument that I'm supposed to be supporting better.
And so to all these different roles that that are available to you know, at an observatory to contribute to the success and the efficiency of observing and producing this amazing data is one of the things that, of course, we really want to highlight. Astronomers are absolutely critical to an observatory, as are the other roles. How might we find out more about the various roles there are at Gemini Observatory? Is there, I'm looking on the kind of the science page, and it has a list of you know, the staff scientists and things. But if we wanted to find out more about the various roles, where would we find that?
Okay, so there's a pamphlet that Gemini put out a long time ago. It must have been 7 or 8 years ago, that highlights some of the different roles of at an observatory. And so I don't know if that pamphlet is online anywhere, but that's something, typically if we go out to schools, for example, we'll hand that out, because that's really important for people to understand that, you know, you don't necessarily have to take a traditional role to arrive at the observatory. If you love science in any capacity, that the observatory will welcome you in some role. And so again, yeah, we have people from all different backgrounds, and that's represented on that pamphlet. And certainly, Jamika, this is something we should do at some point is to make a set of videos to interview people of different roles at Gemini Observatory.
There was an interview done recently.
Oh, yeah?
Yeah, it was conducted internally, but made available on the external website, and it highlights all the different roles that make, the end product, etc. So I can try to find it.
Yeah. Is
Okay.
that our public-facing website?
Let me find it. I'll let you know.
Oh, thanks so much, Jen. I'm perusing through the norlab.edu. Of course, the International Gemini Observatory is a part of NORLab. Okay, but Jen, since you know what you're looking for, I'm gonna let you do that. And while we're doing that, first, of course, anyone in the chat, please feel free to drop questions or comments there, as we are really have the attention of the observing team right now. So all of your questions, any thoughts you may have about any aspect of observing instrumentation, any of that, let us know. And so I really like to, while you are looking for that, Garima, you mentioned the GPI-2 instrument, and Brian and Charlie also said that instruments are actually mounted onto Gemini. Could you maybe talk a little bit about GPI-2? This is the Gemini Planet Imager. Is this for exoplanets?
Yes, I can definitely talk about it. So GPI was originally a Gemini South Chile, and it was I think it operated for like 6 years, if I'm not mistaken, and it discovered a planet. It's incredibly hard to take images of exoplanets. So GPI is going under upgrade right now because the technology on GPI-1 was kind of like, if I'm not mistaken, a decade old or even older than that. And so now we have new ways of doing this technology. I mean, there's a lot goes on in when you take direct images of exoplanets. You need to have like a faster adaptive optics. You need to have low readout noise camera so that you can actually see the images of planets in your, you need fast detectors. So GPI is going under upgrade in the US, and now it's going to be moving to Gemini North. And the hope is that with new upgraded technology, we would be able to see more planets. So exoplanets are basically, I'm just going to repeat myself, planets that orbit stars other than the sun. And if I'm not mistaken, as of now, we know roughly 5,000, or I think more than 5,000 of them. And most of them were discovered using Kepler Space Telescope and TESS. So these planets were discovered mostly with indirect detection. So you don't really see the planet, but you see the influence. You kind of study the influence of a planet on its star. So you monitor the star itself. So we were able to find a lot of planets through indirect detections. So through Kepler and TESS telescope, which are in space. And direct imaging is as the name suggests, you directly take images of exoplanets, and that's what GPI is all about. And we have roughly 3 or 4 facility class instruments on the planet Earth. So we have like one instrument called Sphere, which is at BLT. There's one next door, Skexeo, which is at Subaru. And Gemini is gonna get GPI, and we have KPIC at Keck. We have another one at Magellan telescope. So there are only like a couple of instruments which are there on the planet which are trying to take more and more images of exoplanets. So Gemini North is gonna receive GPI in about a year. And so part of my job is to basically do the verification and commissioning of this instrument. So to make sure that it's doing what it's supposed to do, that all the science and technical requirements are met. And so it's my job to say yes to Gemini, that yes, it's gonna work and it's gonna do what it's supposed to do. And we can offer it to the, to the science community. That's kind of like why I'm here.
Can I play devil's advocate for a second? Why the heck would we want to see them when we can directly detect them? It seems like it's much easier to directly detect them. So why not just stick with that and not? Because pretty pictures are great, but who cares?
Dang, baby.
So I think direct imaging is a complementary technique to all the other methods, because you can see the snapshot of the whole family of an extrasolar system. And you can also image the circumstellar environment in which these planets fall. So you can see the Debye disk or transitional disk. That's something which is very pleasing to eyes, as well as like you can test your planetary formation models if you have the direct imaging data. That's something, so it's a complementary technique.
It's also complementary in a capacity that allows you to see planets that aren't easily detectable
With the indirect detection.
with those indirect methods.
Yes, so direct imaging can find easily image planets which are further than the sun, Saturn distance. So they are like beyond 10 AU. And indirect detection techniques, they're more sensitive to finding planets which are within like 5 AU. Because then you can
5 times the Earth's sun distance.
Yes. So direct imaging has a lot of complementary, getting the word, but yeah, it kind of like completes the picture.
Nice. And yeah, I
And
guess
it makes
so.
for pretty pictures.
Yeah, totally. Yeah, I mean
Seeing is believing.
that's why we're all here, right? It's pretty
Right.
picture.
Well, I mean, it's very satisfying when you see repeated images, repeated observations. You can actually see the planet
Exactly.
orbiting the star.
Right. But it's a unique scientific phase space too, because you do get to get a higher chance of detection, things that would ultimately maybe be in the noise or would be very difficult to detect, especially at large distances, and I guess low mass as well, right?
Yes. Yes.
Are there any other science cases that are not exoplanet detection at GPI would be good for?
Yes, I think it's gonna look at the moves of our solar system, and it's also gonna
Okay.
image asteroids. That's what I'm
Very cool.
What about like quasar host galaxies?
I think there is a science case on AGN.
Yeah, because I mean it's the same kind of thing, right? Like so you have really bright
Object that you can block
exactly.
and then see the faint
That would be
structure around it. Yes.
Yeah.
What's the field of view on GPI 2?
It's a great question, and I
Okay.
think this number may not be correct, but I think it's 25 by 25 arcsecond field of view. That's the
Okay.
IFS of GPI.
It's really large.
Yeah.
But I should double check that number.
Can I, Garima, I have the link here to GPI 2, and then we'll come back to the day in the life of an observatory. Jen sent me that link, and we have the videos. We'll come to that next. But before we do that, is it okay if I share my screen and we can maybe look at some of the specs of GPI 2, Garima?
Just to interject, yeah, so there was a question in the chat about the wind speed, which is of course why we're all
Yes.
here.
All right.
Just about the wind speed.
Thank you.
And
Thank you.
it hasn't improved very much, if at all. So
No.
yeah, we're
It's
still,
all over the place.
It's it's pretty gusty up there. So we're gonna talk story for a little bit longer.
Is this typical weather at this time of the year where we can expect these kinds of wind gusts, or is this kind of just in general throughout the year at the summit, you can get these really high wind speeds?
I feel like we're more likely to see some of the high winds, poor conditions around this time. They can happen anytime, but I think we are closed for wind comparatively rarely. Usually if we're closed for weather, it's due to high humidity. Humidity gets above 85%, we close until the humidity drops below 75 for long enough. But wind speed is a much more rare issue, and the wind has been pretty fierce for several days now and looks to be that way for several days more.
Affecting the whole island, not just the summit.
Sure.
We have different wind conditions if there's ice on the dome.
Not really.
Keck definitely does.
Different wind conditions?
Yeah.
Different wind limits. No, wind limits are.
Yeah, I guess.
No, but they want to point the ice towards the wind so it can help sublimate,
Yeah,
get rid
okay.
of the ice.
Yeah, okay. Yeah, because Keck's wind conditions drop by a factor of 2 or 3 if there's ice on the dome. So I've been on nights like that, classical nights, where wind speed is like 15 miles an hour, and it's a beautiful night, and we can't open.
Is they're afraid of the wind chunks breaking off and coming into the dome?
Exactly. Yeah. But the ice doesn't get off their dome as quickly as it does our dome.
And on Subaru, if there's snow, then the wind can very easily, because it's a flat
top.
Yep.
very easily just get pushed right out.
Yeah, we don't have. We're not a can.
Not a can.
Versus what are the telescopes that literally shake it off? It's not us, right? There's a telescope up there that when they get snow later in the night, they just shake the dome to get it all to fall off.
Oh, really?
VLBI, if VLBI collects snow, they'll tip over and dump.
Yeah.
Radio telescopes.
SMA, we would climb up and actually brush it off with a
I'm surprised you can't just dump on SMA too.
yeah, I don't think it turns that far.
My experience with radio astronomy, you'd have cases where you would have to dump the snow out of the dish, and you tilt the dish down as far as you can make it, and usually snow would tend to slide out. If it didn't, operators were equipped with a rubber mallet.
Yeah.
And you'd go back and just give the dish a few wraps. You wanted to make sure you learned very quickly that you did that from the back side of the dish. You bang on the backup structure of the dish. Otherwise, you end up a snowman.
Or like RTF, their ability to rotate the dome, so they attached a come along, and every time the tracking went too far, they went
Crank it along.
cranked the come along to get the dome to turn.
Wow, that's a really creative approach.
Yeah. So I guess whatever it takes, you go back to ancient methods sometimes just to get your observations.
If I could tell one more snow removal story, the old 300-foot radio telescope at Green Bank, West Virginia, they had a very unique way of removing snow. They tried a number of methods. It was a very large dish, and it did not bend over enough. It could not lower enough to dump snow. Early on in its lifetime, it had a mesh surface. And so they tried building bonfires underneath to melt the snow. But because it was a mesh, the melting snow would rain it, would fall on the fire and put it out. They actually got a hold of a jet engine from an old fighter plane, and they put it on a cart. And they basically used it as a massive heat gun. And it worked. And it was, as you can guess, incredibly noisy. It worked really well, but they had to essentially hire a person full time because maintenance of the thing was so incredibly difficult. But a jet engine, an observatory that had a jet engine to remove snow, I think was probably the best thing I'd ever seen.
That's incredible. That should do it. That'll melt it.
That'll melt it. We don't have that problem, fortunately.
I forgot SMA does have heaters underneath their dishes.
Yeah.
Yeah.
That helps.
Wow. Wow. All right. So moving from snow stories, because I'm feeling a little cold now. Let's take a look at G Pi 2. I'm gonna share my screen, Karima, and let's see what we can find out here. Can you see my screen?
Yes.
Okay. Um, and so it's assessed that, you know, GPI 2 is an upgrade to the GPI instrument, as you said, that was previously at Gemini South. I'm going to go down here to the instrument design, of course, and we see you, Garima, here as part of the GPI team, along with quite a few others. Could you maybe take us through the team and how you all work together?
Sure, why not? So on the screen, the first name that you see, Jeff, he's the PI of GPI 2. So, so when you're within Gemini, you kind of like address the teams as the external partners. So Jeff is the external partner. So he's a GPI 2 project lead for the PI, the principal investigator. So he's the one who is leading the upgrade of GPI, so the GPI 2. Quinn, the name that you see, Quinn and Bruce and Dimitri, they are all like they are all GPI 2 lead. So they are basically taking care of certain aspect of the upgrade. For example, the team of Quinn at UC San Diego, it involved she and her team are basically working on upgrading the wavefront sensor for GPI. So they're going from Shack-Hatman to pyramid wavefront sensor. Bruce is he's one of the, he's well known in high contrast imaging of exoplanet field. So he knows everything. So he's kind of like overlooking GPI 2 and guiding everybody who is actually, the main team who are developing and upgrading the instrument.
He's also
And-
the UCO director, which is pretty impressive that he's able to do all of that in terms of leadership role and then also have extra time to do GPI stuff.
I agree with you. Yeah, he knows everything. And Dimitri also is a part of the GPI 2 lead, and if I'm not mistaken, he is also working on improving the I think focal plane wavefront sensor for GPI. So all of the things that I'm saying is to improve the image quality of GPI so that you can see less noise and more planet signal. OQ is the project manager within Gemini. So I work directly with her. So she's a project manager. I'm the project scientist. So she's basically making sure that the overall managerial aspect of the instrument is met within Gemini and everything is within the budget, within the scope of the instrument. Theo is the instrument scientist. So when the GPI 2 instrument will be commissioned, then he will be the one, if I'm not mistaken, he's gonna basically close all the loop and then run the instrument. And my job, well, I'm an AO scientist, and my job is to basically make sure that all the, well, I think I'm repeating myself, but all the science and technical requirements are met. And if, let's say, so we can imagine like, if this was like a GPI 2 observing night, and let's say Theo is kind of like closing the loop and, making sure that, we are on the target. And if, let's say, something doesn't work with the instrument itself, like say wavefront sensor is not doing its job, or the DM is, the deformable mirror is not closing the loop, then it's my job to figure out what's wrong and how to fix that.
Freeman, might you explain what closing the loop
Oh yeah, sorry.
in terms of AO science and just kind of like what adaptive optics is in
Yes.
general might be helpful.
So adaptive optics basically is, I think Brian kind of touched upon it. When the light from the astronomical object enters the Earth atmosphere, the light of the star planet system kind of get it scatters around. And the telescope basically, when receive the light, it doesn't create the best image that it's supposed to produce. So adaptive optics basically undo the effect of the Earth atmosphere. So it untwinkles a star. So and what goes around, AO basically has wavefront sensors and deformable mirrors to basically untwinkle the star. So wavefront sensors are basically sense the aberration in the image. Or maybe I can explain it in a different way. There's an example that I usually give, like you are taking a shower and you have two knobs for hot water and cold water. So this is like an easy way to explain how AO works. So your body, in this example, is a sensor because your body is sensing the temperature of the water. And the hot and cold knobs are basically wavefront sensors. So, and your mind is a controller. So basically what's happening is like when you turn on the hot knob, your mind kind of like your body basically sends a signal to mind saying that, hey, it's too hot. Okay, let's, turn on the cold knob. So this is like a feedback closed loop system. So my body senses the temperature, and then my mind, which is a controller, sends command to my hands to kind of like turn on the hot one or the cold one. So that's like the closed loop system. So that's how I explain AO basically. So your wavefront sensor senses the aberration that the atmosphere introduced into the light path, and deformable mirror basically corrects for those aberrations. And deformable mirror, in short, DM, is basically a piece of thin glass supported by a bunch of actuators that can shape the mirror. So DM, when you close the loop with adaptive optics, your wavefront sensor constantly sensing the aberration in your light path, and DM basically corrects for those aberrations to undo the effect of the atmosphere. So GPI-2 is an extreme adaptive optic system. So,
And unlike in your shower analogy, it's
Yeah.
doing it 1,000 times per second
yes,
or
yeah.
right?
Exactly. So AO basically, the sensing and correction is happening 1,000 times per second. So it has to be fast. So if you have like high wind speed, which is like, an AO system can go to a certain speed, like, 1,000 times or 2,000 times per second. If you have a very high wind speed, sometimes your AO system cannot actually correct for those aberrations because it's beyond the speed of the AO system. So that's why sometimes, like, even if you're observing under high wind speed condition, you're not gonna have a good AO correction, so your image quality would be bad. So that's like one reason why high wind speed is bad.
The making a correction and then I guess it's too late, so it becomes an over correction that now has to be compensated for the next.
Yes. So when you have high wind speed, you're basically not measuring the aberration in real time. So you're correcting what was measured before. So your correction is not good, and your image quality is still bad. So so a GPI-2 is an extreme AO system. So GPI-2 not only does adaptive optics, but it does something else, which we call coronagraphy. So when you take direct images of exoplanets, it's incredibly hard to see a faint planetary signal around a very overwhelmingly bright star. So you would have to kind of like switch off or turn off the light of the star, but you can't turn on the light of the star, but you can block it within your instrument. So GPI-2 will have a coronagraph that's like an opaque. Normally, like coronagraph is like an opaque disk that you can put at the focal plane of your telescope to block the light of the star. So when your system has an adaptive optics, coronagraphy, and a bunch of other also sophisticated algorithm. That's called extreme adaptive optics. So that's what GPI2 is all about. So again, when the instrument will be here, then I'll be making sure that the AO loop is working well, coronagraphs are blocking the light of the star properly, and all the rest of the node in your images are also like kind of suppressed so that you can see penetrating signalish.
Thank you
Nice.
so much for that, for the detailed insight there. Wow, that's a lot.
No,
That is
great.
That's so much. It's incredible how well how much goes into these instruments to make sure they actually are performing up to their specifications. And if I go back to, I'm going to share my screen one more time. It says here that first light is expected late 2024, early 2025, which you alluded to. What is first light?
First light is when the instrument sees the first light or the light at the telescope. So the very first night when the instrument kind of like look at when the telescope and instrument together, they're looking up at the sky and then receive the light. The detector receives the light, and that's called first light.
When did computers become fast enough to be able to do the real-time corrections for it?
So we are already doing, we already have like, it's a good question. We do have the vision RPC. I don't know the.
I think the first the first AO system that I know about was on Lick, and it was started around 2001 or so. So at that point, they were testing the laser system that Keck is currently using, and I mean, I think they were correcting 1,000 times a second, and so there was clearly capability at that point. So it's been several decades, and I mean, it was a program that came out of like top secret Reagan stuff in the 80s, right? So yeah, I guess military at least had computational power at some point.
I suspect, I have a hunch that deforming the mirror may have been the higher hurdle, a higher hurdle than the actual computational power.
Mhm.
The goal, if I talk about extreme here, the goal is to run DM 4,000 times per second. But that's a stretch, that's ambitious. But if we can run the DM that fast, means we can basically correct the faster.
But that's the goal. That's the goal for GPI2.
The extreme, yes.
So does GPI2 has its own adaptive optic system? Is it used in conjunction with the telescope's adaptive optic, or is it standalone?
No, it's a standalone.
Okay.
GPI2 will use its own AO system, and it won't even use GNAO. GNAO is a new adaptive optic system for Gemini North that's been out 5 to 6 years.
Right.
So GPI2 is all standalone. It's not using. It's bringing its own things.
How big is the deformable mirror, and how many actuators are on it?
So GPI2 is going to use previous DM that they had GPI1, and it has some dead actuators as well. And I think question, it's a DM's 64 by 64 DM. I should double check that. It's a MEMS DM. 64 by 64. And we have actuators.
Oh wow, okay, a lot.
I should double check that. Either it's 32 by 32 or 64 by 64. But there are some dead actuators, which means that light would leak in the image. Kind of image those place where the actuator is dead.
You can't replace those, or it's too expensive, or what?
It's too you can't replace. Would have to buy. Yeah, or I think you can replace it like it's
Oh really?
I don't know what really goes on behind that. Might have to just remove the electronic where the actuator is dead, but I should double check. Maybe it's too expensive or they don't have time.
Yeah.
Do all observatories use adaptive optics to make sure that they get the best image possible?
So there's something called R0, which is called the coherence length. So at Maunakea, the coherence length is like, if I'm not mistaken, 20 or 25 centimeter. So if you have a telescope of 25 centimeter size or a 10 meter, they would produce same quality image if the 10 meter telescope does not have a NIFS system. It's because that coherence length, what it means is that patch in the atmosphere where all the points of light is in phase. So they would create, like if you have a 25 centimeter telescope or a 10 meter telescope, it's not going to make a difference. So you need to have an AO system to be able to basically. I'm not sure if I'm explaining it well.
No, it's great.
But that coherence length is dependent on the wavelength that you're observing.
Yes,
right?
it
So it
depends on
changes
the
quite a bit
wavelength.
from like optical blue to as far in the infrared as we can see.
Yes, and it depends on from site to site. It's not like one absolute value. It depends. So on Maunakea, all the telescope have a system, and if you have a bigger telescope, you must have an AO system. Otherwise, there's no point. You won't be able to get the theoretical image of a telescope. Theoretical image that your telescope is supposed to.
Well, it depends on which type of science you're trying to do, right? So I mean,
that's true, yes.
so supposing you're trying to do spectroscopy, where you're just the zeroth order, you're just piping light through a slit, and then you're dispersing the white light into its constituent colors. In that case, making that image as tight as possible is not as important. It's still important because the surface brightness limited, but it's not as important as something like direct planet imaging. So it truly depends on, I mean, there's plenty of instruments even on Maunakea telescopes that don't use adaptive optics because it's not strictly necessary. And in fact, one instrument that's just going on Subaru is the prime focus spectrograph, where there's these fibers and it covers a huge part of the sky. And in those cases, these things are just acting as light buckets, and they have, let's say, a 2 arc second aperture. I don't know what they actually are, but you're just throwing light into that fiber and then you're dispersing the light. And so that case, AO is not important actually at all.
You're absolutely right. It depends on Brian is right. It depends on the science cases you have.
But every observatory could use an adaptive optics system because there's always scientific space that requires it, or that it's significantly enhanced by adaptive optics.
If you want to resolve features, then you need AO to close the loop on you. Like if you're looking at the moons of solar system, in seeing limited conditions, you won't be able to see details. So if you need details, so it depends on the science case that Brian suggested.
And it depends on wavelength.
Yeah.
And it depends,
Sorry?
And it depends on wavelength, because optical and infrared telescopes need that, sub-millimeter and radio do not.
Yeah, right. And we can't even do adaptive optics in the optical currently.
Yes,
I mean,
yes.
it will become in the future, but currently, so right now we use it exclusively in the near infrared. So the optical light is piped to the AO system, and the infrared light is piped to our instrument. And so like the prime focus spectrograph is an optical instrument, and so it couldn't even use adaptive optics if it tried. So it's designed to not use adaptive optics, in part for that reason. Right, but you want to have the largest breadth of capability, because there's so many things happening in the universe. There's so many different perspectives, so many different scientists that come from so many different backgrounds and have so many great ideas. And as an observatory, we want to be ready with all the, as many capabilities as possible so that people can take advantage. Because if we don't, somebody else will innovate, and then, and people will go to those observatories to use their facilities. And so the idea is that we provide, unique capabilities, but also kind of the standard suite of capabilities. And so Gemini is the kind of lithe, agile telescope up on Maunakea. And so we want to have, you know, a large breadth of capabilities so that we can be ready for kind of any science that people ask for.
Incredible. Incredible. It's a great segue into a day in the life of an observatory. Thank you so much, you all, for those insights. Garima into GPI2 and very detailed conversation about adaptive optics. There was quite a bit that I did not know, like that you can't use it in the optical. I did not realize that. At least right now. And so I have to say, we look forward to GPI2 coming online, and hopefully at that time we can follow back up with you, Garima, and the rest of the GPI2 team after you have first light, so we can get some insights on the exciting science that GPI2 will be doing. So in the chat here, I have a day in the life of an observatory, and I'm going to play that video if that's okay. It's about 2 minutes long. And Jen, Charlie, Garima, Brian, after that, everyone is welcome to share your insights after we look at this. Okay, so here we go. Let me know if you can hear me. Let me try this one more time. Yes, there we go. Okay. Okay. Okay, I'm gonna stop my share. Thank you so much, Jen, for that link. And this is part of the NORLab Stories blog. And Jen, you are featured there.
Yeah.
Would you care to share a little bit about maybe the making of this? And then we got to see, it looked like different control rooms. It wasn't necessarily Gemini's, and so yeah, maybe you can talk about what we saw there.
Okay, I only know a little bit about the small part I took, but basically, NOIR was looking to figure out all the different types of people that work to make these facilities run across all of NOIR, and there's a lot of different telescopes and facilities that contribute our NOIR. So yeah, they were just picking different roles to get an overall feel of the types of jobs that are available and the types of tasks that are being completed at many different levels across the observatories. So, and how that unites all of us, I guess, in a sense, because we're all working towards one purpose, and that is to get science.
No.
Yeah, no, this is so great. I'm so glad that you shared this. So this is, yes, it's a look into the diverse team of people who keep NORAD observatories running 24/7. And so, of course, right now, this evening, we are with you all, and it's, fantastic to with your group at the Gemini North to see the variety of roles that it takes to make the observatory work during the daytime, the day crew, and all of those roles, and then to the evening. And one of the things that's highlighted in the blog portion, Jen, is that you work. Let's see. It says you act as a bridge between daytime and nighttime work, which officially transitions around 4 p.m. during astronomical twilight. And we did hear Charlie mention astronomical twilight. And so, what is that? What is that like? That transition?
Okay, so for this particular article, I was speaking for the SOS daytime position. And what we're doing for that is we're basically we are the liaison between the day crew and then the instrument team who wants to get done their work during the day as well, and preparations for the night. Anybody who wants to use the telescope goes through ASOS to make sure that there's no conflicts that could lead to things breaking or injury. And then meanwhile, when things, when whatever they're working on at the summit takes a pause or they're finished, I'm able to do my calibrations and my preparations for the instruments that are going to be prepared for that night. Looking for any reboots or any potential problems that I can make a note of so that when the night gets here, everything's set up and ready for them to go with the least problems possible. And they're fully informed because they've been sleeping all day. So they're not around for all the stuff that happens during the day, and they can get caught up and get to work quickly and get on sky.
That seems like a really important role. To connect the day crew and night crew so that everyone is aware of what's going on. And so is that a role that you kind of transition in and out of, because you're here with us in the evening in the operator role? Do you switch hats?
Yeah, so if we're working night shifts, they want to make sure that we are not losing our minds, and so we get some time off after our night shifts. So for 5 days of night shifts, we get, let's say, about 5 days of recovery time. And during that time, we are getting ready to maybe work for a 5-day daytime shift. And we'll arrive in the morning along with everybody else, attend the morning meetings, check some of the data from the night before to make sure anything doesn't be done before the telescope moves. And yeah, basically starting up that role of the hub of communication, I guess you could say, for the day. And then so yeah, we'll do maybe 3 to 5 shifts of that. We're also doing some mask cutting preparations for masks that get sent to the summit. And then after that, we could basically transition straight into a night shift after a 5-day day shift. And the night shifts are somewhere between 11 to 14 hours of work every night, whereas the day shifts are more of a 9 to 5 type job. And so the SOS does have a wide range of responsibilities, and we do shift between them. So observer, for one shift, operator for another shift, ASOS for another.
Incredible. Thank you so much for giving us insight into the various roles that you play, Jen, and also how that connects everyone to make sure that things go smoothly. And in these last few minutes, I'd like to maybe jump over to Charlie and Jen also. You were both just recently at the American Astronomical Society meeting. And one of the things that you do is talk about all of the capabilities of Gemini and highlight the instrumentation. And one of the things that is really important, of course, is the data scientist, the coding, being able to analyze the data, do data reduction. And I had the honor of listening to Charlie's I-posted presentation, which was fantastic. And it was on a program that you're working on to help with data analysis. Could you give us a bit of insight into that, Charlie?
Sure, I could, I don't know if I can share my screen or not.
I believe.
Can. Looks like I can. I will try to show you. I'll show you what I've been working on here. So one of our tasks as observer, as operator as well, but essentially night crew, is to assess the data as it comes in to make sure that we are getting the highest quality data, that we are getting data which makes that makes sense essentially, so that the researcher can do their job. And there are limits to how we can assess that, but we need to be able to look at it very quickly, make sure we're getting light from the source, from the target of the observation, that we're not saturating. If the detector saturates, then we're losing information in that. And so we need to be able to look at images very quickly as the data comes in, as we're taking many observations, many actual exposures over the course of the night. So what I was presenting at the American Astronomical Society meeting was my work in a viewer that is able to do some basic processing aimed specifically for our use on a nightly basis. You could use this anytime you wanted, but to look at astronomical data. But it's very good for us as an observer, in particular, to be able to review the data as it comes in. And so, for example, this is what you're seeing on your screen is the basic program, and a large part of this I did not write. It's a viewer written by a fellow at Subaru, but viewer is called Ginga, which is the Japanese word for galaxy. Subaru is a project of the Japanese Space Agency. But what I did is write a plugin to that enables us to review our data, to process it in a way that makes sense for us. So, for example, the view you see here is an image from our GMOS detector, and it's a little bit of a complicated data file because there are essentially 8 pieces of this image that have to be stitched together to form a complete image. And this is when the new data file gets written to the data directory, my program here, SeqPlot, is going to be able to tell that a new data file was written and automatically load that up. But it's not just going to load it up, it's going to tile those 8 components together so you can see that full picture. And I really like this picture because, I mean, it's a really nice star field here. There's also a kind of interesting bit. This funny little shape over to the side here is actually the shadow of the guider that we use. That guider helps make sure that the telescope is pointing at a constant location, that it doesn't drift by even small amounts over the course of the observation. But if I zoom in here a little bit, you can see we've got a couple of interesting characteristics here. We've got some straight lines that are cosmic ray traces. We see this very bright line that runs vertical through the frame. That's actually a hot pixel on the GMOS detector, and that's fairly normal. You can also see this red color here, and that's indicating that there's saturation, that there's very high value there. some of the stars, you can see that little red center in there. That's got a very means that that we have saturation at those stellar images. But one of the things we can do with this very quickly is we can manipulate the image very simply. So I can rescale the image here, and I can see that there's actually a lot more stars there that we're looking at than you would have been able to tell previously. And actually here you can see those 8 sections as vertical stripes left to right. Each one of those stripes is stored as a separate piece of the data file, and so they have to be tiled together. As an observer, I'm going to want to be looking at this, making sure that the principal areas are not saturated. A little bit of saturation in some of the stars is not a problem, but the science target we want to make sure is not saturated. But we can go from image to image to take a look at, as the data comes in. This is one of my favorite images. You've got this big oblong, this is obvious. This is a GMOS image as well. It's only made up of 2 stripes. But you can see there's this big oblong shape here. That is a real thing. And you might be able to guess what that is. With that kind of a profile, that's most likely a galaxy. But what's really interesting, what I really like about this is my program makes it very easy to rescale the brightness levels. And so I can zoom in on this and rescale. And there we not only see, there's our galaxy. We've got a nice galactic core, nucleus of the galaxy. You can even see arm structure here in the galaxy. But we've got this bright object right about the center of the frame, and that actually is a brand new supernova in that galaxy. That supernova has a comparable brightness to the whole galaxy itself, really. For that brief period of time, for a few days, weeks of that afterglow. But basically, this kind of tool makes it it simplifies our job as observers as we're trying to assess the data that's coming in.
And Charlie, this is the thing that's at 2 o'clock from the center?
So right now, in that image, the supernova is actually right about the center of the image there. I mean, so that whole image, so there's an orange box. It's about 2 o'clock from the center of the orange box, but it's sort of dead center of the image itself.
Got it. So it's 2 o'clock from the center of the galaxy and the center of the orange box.
About that, yeah, exactly.
Got it. I see it. It's the brightest. I see what you mean about. And it's hard to tell, but there's more light, you're saying, in that point source than the rest of the galaxy put together?
Typically it's as bright as the whole that supernova is typically as bright as the whole galaxy that it is a resident of, or was a resident of, that it occurred in. I'll say that. I don't know for sure for this one. Actually, the tool does not have capability of making that measurement. That's a much more advanced kind of data result that you'd want to look at with a much more sophisticated data processing. This is not supposed to be a tool that's going to allow you to do your science from. This is a quick viewer for our role here as the night crew. The full image reduction, which would clean up the image substantially, is a much more involved process. And I'll point out here, for the sake of everyone else involved, that the data we see here is essentially more monochromatic. It's essentially black and white. The colors that you see here are completely false colors, chosen for their contrast to make it easier to distinguish differences.
If I'm not incorrect, so this is a GMOS image.
This is a GMOS image.
But it's an acquisition image to set up for.
Correct.
So in the end, there will be an observation probably the next observation.
Correct.
Be placing-
So
you
let
can
me,
see it dark.
yeah, I can even, let me show you here. I'm going to zoom back. I'm going to zoom back out on the image. Well, I didn't really mean to do it that way. I'm going to leave that zoomed in. All right. So you can see there's our supernova right there at the dead center of this image. If we go on to this is as Brian mentioned, is an acquisition frame. This makes sure that we're pointing at the right target. The next frame we see, if I go on to the next one, is a slit image. It shows us exactly where the slit is located. And you can tell probably by eye that those things are lined up pretty well. And if I go to the next image, we're actually looking through the slit at that supernova. Let me see if I can adjust our contrast levels here a little bit. So there you can see the edge of that slit. You can see that supernova right there. And so we go through these steps. We look at a field image. So we just look at the sky. So make sure we're centered on target. We look and see what the slit looks like. And then we take an image through the slit to make sure everything is lined up correctly. And then after we've got that all lined up, then we start actually taking the science. And let me see if I can show you. So this is what that's basically what that science is going to look like. These are spectra. Wavelength from left to right. Let's see if we can see a little more clearly here. But basically, how bright, how the regions that are brighter or darker are going to tell the researchers something about the composition of that luminous material. And they're going to fit that in with their models of supernova events and allow them to. Actually, that looks more like a flat field, doesn't it?
You got flat.
Yeah, I see it. Let me go on. Let me try the next one. There we go.
Yeah.
There's a science frame. And you can see here these
The night
bright
sky
lines
and-
are indicative of different elements that are present in that expanded material from the supernova explosion.
Is it a single long slit?
Say again?
Single long slit.
Single long
This is
slit?
this is a single long slit observation.
And those partitions are just detectors on GMOS?
So there's 3 detectors, and you can see that there's I don't know if you can see my cursor here or not. There's
Yeah, I see it.
there are these dark bands, these 2 dark vertical bands that are the separations between the detectors. There are 8 amplifiers among those detectors, and those 8 amplifiers are actually what's producing the vertical stripes.
Gotcha.
And what are those? There's lots of little things.
All the snow.
Yeah, the snow is.
Yeah, so
is part
those
of
are
that?
cosmic. Those are cosmic ray traces. So cosmic rays are high energy particles from the universe as a whole. Many of them are produced in supernova or other energetic events. They move very quickly. They hit our atmosphere and they cascade into showers of subatomic particles, and they shower down all over the place. But they will expose detectors. And so that's noise that actually needs to get removed from the data before the data is analyzed for scientific use. And that's part of the thing that a proper data reduction does. It'll remove those things. It's not important for us to remove those. You can't, they're always going to be present in some form or another, in some random pattern. The longer the exposure is, the more of them you're going to collect over the timeline, over the length of that exposure. It's not important for us as an observer to remove them, and it's a little bit of a computation-intensive process to do that. So I don't even worry about that in the program here. Here we're trying to make sure that we're not seeing saturation in the data, that the spectra look nice and clean. That kind of thing. And that's one of the things that this software tool is good for.
Incredible. Absolutely amazing. This is just, an incredible tool, clearly, Charlie. And so how long have you been using this, or is this something new?
So this is fairly new. We first started using it on Sky in June of this past year. And it's been in use on and off since then. We're actually not using it at the moment as we're collecting data right now. I mean, if we were open, we wouldn't be using it at the moment due to some software issues that we have. But essentially, it is otherwise has been in use since June and is proving to be a very, if I do say so myself, is proving to be a very beneficial tool.
I agree. Yeah.
The fact that we can't use it right at the moment has been very frustrating to me as an observer. I've got, in that short amount of time, I got very used to what it could do for me.
Yeah. And we do have a program that is somewhat similar to it, but it doesn't have near the capabilities that Charlie's program does. The ease of use is not there, the adaptability is not there, and some of the new functions that we have coming online with the observatory, those aren't integrated into the old software. So Charlie's tool is, for commissioning, for new capabilities that I'm involved in, Charlie's tool has been invaluable to be able to reconstruct, for example, paint chips on our pickup.
Yeah.
But in many aspects of our observing either daytime work or nighttime work, we use Charlie's tool to great effect. So we're very much hoping that those software issues go away shortly, and then we can start taking full advantage of Charlie's tool again.
Well, I hope so too, and I certainly look forward to hearing more about this amazing resource, Charlie. Hopefully in one of our upcoming sessions with you all. And I know we're a little bit over time, and so thank you so much for your patience and for staying with us, allowing us to stay with you. And so as we wrap up, I'll hand it over to Brian to maybe give us a last look at those wind speeds and weather, and when we can possibly catch up with you all next.
Yeah, thanks, Jamika. Well, thank you as always for being our guide through the night and just being an amazing presence on these sessions. And I see Raja joined, so thank you, Raja, for making this program possible and for everything you've done for this program. Yeah, so unfortunately we're still closed. This is the reality of astronomical observing. We stay here and we hope for something. Sometimes it materializes, sometimes not. But we're well prepared in case anything, the wind speeds abate a bit and do some observing. That won't be on this session, but maybe later tonight. We have a session coming up on Tuesday. It's a dedicated session. So it won't be public for everybody, but we plan to do probably 2 public sessions per month at Gemini North, and we're any night we're prepared to observe. There's a possibility for a shadow session. So so look for new sessions coming up next month, and I think we'll be doing something in tandem with Journey Through the Universe, which is a program here on Big Island and also in Maui. Which is an outreach program designed to go to high school, middle school, and a little bit of elementary school classrooms, and give students an idea of what it's like to work in an observatory, what kind of science we do, who we are as people. And so this is very well in line with the mission of Shadow the Scientist. So we'll be doing some tandem activities there, and hopefully all throughout the year. So as long as we're open, or as long as we have the possibility to observe, we will be doing shadow sessions. And so please check those out in the future. And unfortunately, yeah, wind speed's still bad, so.
No improvement.
No improvement.
It's been fluctuating, but no improvement.
Yeah, so maybe at some point the observer will call the night.
I'll sign off. Thank you so much.
And I want to say Raja is up early. Raja was at WS, this conference we were just talking about that Charlie was also speaking about. And Raja had a quick turnaround and now is from New Orleans and is now in London. And so thank you for being up so early and popping in. Raja Guhathakarth is the founder of Shadow the Scientist and makes all of this happen. Raja, please, the last words before we sign off.
Whoa. Okay. Last words. Famous last words. Okay. No, I'm actually here to do some crest work with our colleague Abby. So again, it's music to my ears to hear that NOAA Lab will host a couple of these public sessions per month. That's really terrific. Thank you, Brian, for making it happen. I met with a lot of pure NOAA Lab colleagues, Abby in particular. We chatted at WS. I saw Clara there. Looking forward to a steady stream of these. We are setting up now these long-term. We've talked about setting up these long-term partnerships with observatories. Keck, Gemini, Subaru, and Lake are obvious places to start, but we're also talking to Rubin Engineering, TMT Engineering, and GMT Engineering. As just like we have an outreach partnership document, we have a host provider or provider partnership document. So anyway, I'll keep quiet. That's it.
Thank you, Raja. Thanks for waking up and talk to us.
Thank you.
Absolutely.
Okay, thanks, Jamaica. Thanks,
All
everybody.
right. Wish you all a good rest of the evening, and thank you so much for letting us shadow you. Jen, Garima, Charlie, Brian.
Ciao, aloha.
Aloha.
Aloha.